And welcome back. We are continuing our discussion of the Big Bang and what conditions were like in the early universe and how that might lead to further predictions that we can test. And we're thinking about specifically now the first 3 minutes, or the time between fraction of a second and 3 minutes post Big Bang. It is hot enough at this point in the universe's history that fusion can happen, right? We know that at the centers of stars, it's hot enough that fusion happens, although that takes a long time. At the center of the sun, it's 15 million Kelvin. It takes on average 5 billion years for an average hydrogen atom to get fused into a helium nucleus. Obviously, it's a lot hotter in this region of the universe's history than it is at the center of the sun, so this can happen much faster. And so hydrogen atoms can and do fuse into helium atoms. But that's it. Heavier elements don't really get synthesized, even though it's extraordinarily hot. The answer, you might be wondering why. I've asked you. You can think about it if you'd like. But the answer is that in the centers of stars, what happens? Well, you're going from hydrogen fusion, and then the next stage of version of nuclear fusion is helium burning, and that happens at a hotter temperature. And then the next stage happens at a hotter temperature and hotter temperature. And you're going from cooler temperatures to hotter temperatures as you fuse these heavier elements. In the first 3 minutes, you're going in the opposite direction. You're going from a very hot, dense state to a cooler, dense state. And that hydrogen fusion happens at a time when it's hot enough for that to happen, but it's already past hot enough. It's already past a temperature where you would need to get helium burning into carbon. And so because you're heading in the opposite direction, hydrogen atoms do fuse into helium, but heavier elements don't really get synthesized. And so the models actually look something like this. There is, again, if you look at models of particle physics and nuclear physics at the beginning of the universe, they expect that at about 1 second after the Big Bang, there will be for every 7 protons in the universe, there will be about 1 neutron for every 7 protons, 2 neutrons for every 14 protons. That just comes straight out of the physics of the conditions of the early universe. These 2 neutrons, almost all of them get caught up end up in helium nuclei. And the rest of them, the 12 that are remaining, stay as hydrogen. And that is 99% of what happens. You end up with, of these 16 original particles, 12 hydrogen atoms and 1 helium atom. And so a prediction of the Big Bang is that the universe at its outset will be by mass 75% hydrogen, because this helium-4 nucleus is about 4 times the mass of one of these hydrogen nuclei, about 75% hydrogen and about 25% helium by mass. And that almost exactly matches what we see of early universe. Almost exactly 20. In fact, this very closely mimics the composition of the sun. There are a lot of other heavy elements, but it's less than 1% by mass, or about 1% by mass. This is still roughly the distribution of matter in the universe. Now, that's a good sign in itself, but it turns out there are, if you look at the details, very small amounts of deuterium that should be created in the Big Bang. Very small amounts of helium-3 that should be created in the Big Bang. Very small amounts of lithium-7 that should be created in the Big Bang. And interestingly, if you look at, this is a complicated plot, but this is basically the abundance on the y-axis. And on the x-axis is a density of ordinary matter in the universe as percentage of critical density. This is important. Let's come back to this. But this was a free parameter. We didn't know what this was. But we can look and measure the amount of deuterium there was in the beginning of the universe, and helium-3 and lithium-7, and look at that. They agree pretty well, right? The predicted amount of helium-3 matches the abundance. The predicted amount of deuterium matches the abundance at a particular density of 4%. Lithium doesn't match quite as well, and there's an interesting, very interesting reason why that is. If you're interested, this is actually, lithium-7 is one of the things I research. I'm an world's expert in lithium-7. If you're interested in why this is there, we can have a conversation about it. But know that this is probably an observational problem and not a theoretical problem, interestingly. Anyway, they agree beautifully. The Big Bang model predicts the amount of each of these elements that should have been created in the Big Bang. And lo and behold, we go and we see that that amount was created. It's an extraordinarily powerful tool. And interestingly, they predict that only 4% of the critical density of the universe can come from ordinary baryonic atoms, hydrogen, helium, deuterium, any of these normal atoms. Only 4%. Remember, when we went back and we're talking about the constituents of the universe, the visible matter that we could see was 4%. The dark matter that we couldn't see, we could infer its presence, was about 23% of the universe. And lo and behold, we have this prediction which says that ordinary matter should only be about 4%. This is a very powerful argument also for the fact that it can't be, remember our WIMPs versus machos? The machos are massive compact halo objects, things like failed stars and black holes and neutron stars and things like that. That is ordinary matter. I know black holes seem like extraordinary matter, but it had to have formed from ordinary matter, right? And so the fact that we predict that only 4% should be ordinary matter says that dark matter must be something that is non-baryonic. It must be something that is not protons and neutrons and things like that. This is more evidence that in fact the dark matter must be the weakly interacting massive particles. So that's another interesting outcome of this observation. But that is 3 extraordinarily powerful pieces of evidence for the Big Bang. Let us just pause briefly and write these 3 down because this is important. Hey, I got a whiteboard back. What are the 3 pillars of the Big Bang? Well, we already wrote 2 of them down in the last video. I'm going to write down again. One is the Hubble law, the universe is expanding. One is the cosmic microwave background radiation, the fact that we can see the photons that were released in the hot, dense state of the universe still traveling through the universe today. And the final pillar of the Big Bang theory is the primordial nucleosynthesis. I will call it primordial abundances of the elements. The fact that the Big Bang model predicts that we should have a certain amount of hydrogen and helium and deuterium and lithium and helium-3, and we look and those observations that we see, in fact, beautifully match the predictions of the model. Great. Okay, so there are still some mysteries that need explaining, and this is interesting. The Big Bang model, as we've seen it so far, has some interesting problems. One of them is that how is it that so this is an interesting fact. We look at we talked about the spectrum of the cosmic microwave background radiation, and it's there and it's fine. But the interesting thing is that the temperature that we infer, that 2.7, and it's not just 2.7, it's 2.7 plus 3 or 4 extra digits that we have measured it at that accurately to extraordinarily high accuracy, is exactly the same in all directions. Think about that. The temperature of the universe, so we can look in one direction and see almost 14 billion light years away and see the temperature of that stuff, and it's something. And we look at exactly in the opposite direction, 14 billion light years away, and the temperatures of those 2 things are exactly the same. 2 5 significant figures. Now, you might say, what's the universe? That should be the way it is, but there's a thermodynamics problem with this. And that is that in order for, let's say the air in this room or a table or whatever to reach the same temperature, those particles have to interact with one another. They have to exchange energy. That's what temperature really is. It's molecules and atoms bouncing around off of one another. And if you have a cold side of something and a hot side of something, energy will flow from the hot side to the cold side until eventually everything reaches the same temperature. If those two directions of the universe have the same temperature, how is it that that could be? Because they have never, they're only now communicating with us. They could never still have communicated with each other. There is no bouncing around that can be done to thermally equalize the universe and get those 2 points to be the same temperature. Why is the cosmic microwave, that's so succinctly said, how can that background radiation be so uniform in every direction? Why is the density so close to critical? This is another interesting question. I didn't talk about this much, but we said that we live in an almost flat universe, right? When you talk about that capital omega that sets the density parameter, if it's a little bit more than that, it's open. If it's a little bit, sorry, closed. If it's a little less than that, it's open. But that omega equals 1, and it's not just 1, it's 1.01 plus or minus 0.01, right? It's within the uncertainty of being 1.00. Today, it turns out if you go back in time, the universe must be diverging from the critical value, right? So the fact that it's 1.01 or something today says that early in the universe, it must have been 1.00, 10, 20, 30 zeros and a 1. How is it? There's nothing in our theories that says the universe has to be flat. Why is it that our universe is flat? Flat today, why is it flat today? But even more importantly, flat today implies extremely flat early in the universe. Why is that? There's no reason a priori why that has to be the case. And finally, why is the distribution of matter in the universe so uniform? We know it's not uniform on small scales, but on large scales, it's spread out pretty evenly. Okay, so these are 3 problems with the Big Bang model. Let's try to take them one. Is there something we can add to the model that will help all of these problems? And the answer is yes. If early on in the universe's history, it went through an epoch of what we call inflation. So this is a normal expansion of the universe in some sort of linear fashion that we've seen before, right? A normal in linear fashion. We think that early on in the universe underwent some kind of inflation event where it expands by something like 50 orders of magnitude in a fraction of a second. Exponential growth. We know exponential growth from COVID-19 cases this time, right? Doubling every 2 years, every week or so before we flatten the curve. This is flattening the curve, right? But this is an exponential expansion. And if that happens, right? So we can go through 10 to the negative 35 seconds or so for normal sort of expansion, and then it enters an epoch of inflation where in very short order, it expands by 40 orders of magnitude, such that by 10 to the negative 30 seconds, it's 10 to the 40 times larger, right? 10 to the 40 times larger, think about that, right? So think about this, the radius of the visible universe, 10 to the negative 40 meters up to today, where it's something like 10 to the 12 light years, a billion light years, right? Most of that inflation happened between 10 to the negative 35 and 10 to the 30 seconds. Almost all of it. So how does that help us? Again, what causes this? Well, it could be some vacuum energy. I mean, we sort of see this happening now, right? We're sort of in an epoch where the universe's expansion is starting to accelerate. All you need is some repulsive force to get turned on and then turned off. And that's what we think happened. And it might be that when one of these forces separates, like the strong from the electroweak, that this could happen. There are some other theories about specifically what could cause this, but it's not crazy. It's not out of the question, and it helps us in a number of different ways. It solves all 3 of those problems that we were just talking about. Let's talk about the thermal one first. So again, 10 to the negative 38 seconds isn't a long time, but 2 things that are two pieces, A and B, 2 blobs of the universe that are very close together, are thermally in contact for 10 to the negative 38 seconds. That's enough time to exchange information. That's enough time to share energy. That's enough time for these very high energies, for these 2 points A and B, to achieve thermal equilibrium and have the same temperature. Inflation comes and those 2 pieces of the universe gets ripped apart so that they're no longer causally connected. And now we're seeing blob A and blob B separated by billions of light years. But the microwaves that we're getting in the cosmic microwave background from A and B have the same temperature because they did have time to equilibrate before the inflationary model happened. Okay, it can also solve the flatness problem. Why? Because, well, maybe the universe was closed early on, or maybe it was a little bit open, but let's say you have a balloon, right, and you increase its radius by a factor of 10 to the 40. That's not a factor of 40 times. That's a factor of 10 to the 40, a 1 with 40 zeros after it, right? So if the universe was this big before, it's 10 to the 40 times bigger than that. Well, any curvature that you had at all in the early universe, be it positive or negative, we're showing a positively curved universe here, will flatten out to 0, arbitrarily close to 0, 10 to the 40 zeros, right? That's as flat as you want to get it. And so it flattens, it takes whatever geometry was there, be it open, closed, or whatever, and makes it almost perfectly flat. And so that helps solve the flatness problem. It explains why we see a flat universe today. So also it helps to explain some density problems because, again, you're taking what may be a clumpy thing and spreading it out by a factor of 10 to the 40, it looks pretty smooth on that scale. Okay, so we've talked about the cosmic microwave background radiation. I'm gonna pause here and we'll do one more video on the content, and that will be what we think the universe's content is now and where we think it's going. So stay tuned for that.